Hello everyone and welcome to this course on modern application development. Okay, so all the discussion that we have had so far applies mostly to so-called traditional relational database management systems or RDBMS, right? Because we have been talking about table structured data. But you are very likely to have come across this term NoSQL at some point. So what I want to do over here is to sort of go over alternatives to SQL or these kind of databases, and hopefully also make some things a bit more clear about why exactly we call something NoSQL and what are the implications. Okay. So first of all, what is SQL? It's a structured query language. It's used to query databases that have some kind of structure in them. But the query language as such is not tied to a given database. It could even be used for querying spreadsheets, for example, right? So if you look at Google Sheets, there is a variant of SQL that can be used in order to make queries inside a Google Sheet. Okay. Now, having said that, SQL is typically closely tied to RDBMSs, relational database management systems, where you have data being stored in tables with the values actually being in columns or fields of the table, and there can be some tables that hold relationships between other tables. Okay. And the important point over here is every entry in a given table must compulsorily have the same set of columns. This is the definition pretty much, that it has a uniform table structure. So why are these kind of tabular databases used? They are very good at storing data. You have prior knowledge of the data size and you can also do efficient indexing, right? You can basically pick one column out of the different columns in the table and say index on this, right? The database engine basically creates an index, and thereafter any searches on that particular column are going to be faster than they would have been without an index. Okay. Now, what are the problems with tabular databases? They are structured, right, which is usually good, but can also be bad, right? As an example, let's consider that you are trying to create a database to hold student information, right? And at least in IIT, what happens is a student could be either someone who stays in the hostel, right? In which case you need to know which mess they go to and what are their mess fees, have they registered and so on. Or they could be a day scholar, in which case they are probably coming in from outside using their own vehicle, and in which case they need to have a gate pass for the vehicle. Okay. Now, in a regular tabular database, the student table would need to have one column which indicates the mess and another column which indicates the gate pass. Okay. Now, let's say that half the students are hostelers, half are day scholars. I have half the entries in the mess column as null and half the entries in the gate pass column as null. Okay. So is this really an efficient use of space? Obviously not, right? But what can you do about it? The whole idea of a tabular database means that I have to have the same set of columns for every entry. Okay. So this is sort of what got people thinking about how to store data. Are there alternatives? Okay. And a number of alternatives have been proposed, right? So one of them, for example, is a so-called document database, right? So document databases say that a document is essentially some free-form information but with structure, right? So it's not that it's unstructured. On the right here I have an example of a possible document, right? This is basically from Amazon's example for a document database, and there are two, it's basically a JSON file, right, or a JSON object over here. It has two entries. Okay. So this is one entry and this is the second entry. Okay. So the year is common to both of them, the title is also common to both of them, and in fact the information is also common, but within the info we find that okay, plot is, yes, this is also common to both of them, the rating also happens to be common. But what are all these other entries, right? One of them has it, the other doesn't. Okay. Now, a document database basically says that this is perfectly fine. I can have different entries being stored as documents inside this database, right? And those documents are essentially JSON objects, right, which means that any search in it will ultimately return a JSON object corresponding to a particular document. How exactly do I index on it? That's a different story. You would probably say, maybe you can index on the document.info.rating, okay, and then it would go through and find out all the documents that have an entry for document.info.rating and index on those, and other things that don't even have that information would not even show up in that index, right? So that's pretty much all that it says. You are storing data similar to what you would in the other structured database, with the difference being that you no longer have tables of fixed sizes. You are storing arbitrary documents. But how do your searches become efficient? Primarily by the way that you construct indexes, okay? And just like you could construct an index in the previous case, or here too you can take one particular key in the JSON object and decide to construct an index on that if you wanted to make the searches fast, okay? So these are actually very popular these days, right? MongoDB is probably one that you might have heard of at some point. It's also probably one of the most popular in terms of a document database. There are alternatives, and Amazon provides something called DocumentDB for this. You will notice, by the way, that Amazon provides alternatives for every kind of database, right? I mean, because that's their job. I mean, Amazon Web Services is ultimately trying to provide solutions for whatever it is that you're looking for, okay? So MongoDB is an example of a document database. You can see where it differs from a traditional tabular database. And the advantage over here is, let's say, going back to the previous case of students, I would have a student.hosteler.mess or student.dayscholar.gatepass, and they would be completely independent of each other, right? One student would have a hosteler substructure, the other would have a day scholar substructure, and the corresponding entries would be available there, okay? Now there are other ways of storing data. One is called key value, right? And in Python, right, you have come across this notion of dictionaries, right? And what is a dictionary? It basically means that I can sort of have an array where I can say, for example, something like A of apple, right? And I could give it a value red. Now what is happening is that this apple is being taken as an index, right, in order to find some particular location, and in that location I store the value red. Now one way that this is done is actually by using something called a hash table that we already discussed earlier, right? There are other ways. Ultimately all that you need to do is to be able to search for a particular location and then put something there, right? And that search could also be done using other techniques such as binary search trees, okay? So for example, the C++ ordered map is actually implemented as a form of a binary search tree, not as a hash table directly, but the point is it's efficient at implementation and search. It maps a key to a value, and they are very efficient at key lookup but not very good for range type queries, okay? Once again, you might have come across this term called Redis. Redis is usually used as a very efficient key value store. There's also memcached, right, which is used for something similar. The Berkeley DB is something much older but again has a similar kind of behavior. Now one thing that is usually done over here is most of these are implemented in so-called in-memory form, right, meaning that you don't really want these to be things that are stored into external disk. They really have their value when they are sitting completely in the memory of the system and can respond to queries very fast, okay? So for example, something like, if I just want to have a list of students and say, okay, have they finished, have they completed a course, or have they finished enrolling, right, and I retain that in Redis, then the query becomes instantaneous almost, right? I give the student ID and it tells me yes or no whether they have registered. I don't need to go to the main database and look up something. It's much faster. But the problem is it's only a lookup based on an exact query, right? So if I have that kind of thing, they are very fast, much faster than any other kind of database that you can think of, but they have sort of that limited use case. They are very often used alongside other databases, right? So that's what you will notice in practice. There is something called a column store, right? And the idea over here is that traditional databases, sort of, if I had a table, right, I would take all the entries corresponding to one row and store it together, right? So this entire thing would form one block somewhere on disk. This next one would form another block somewhere, okay, which makes it easy to sort of retrieve all the entries corresponding to a given row. But let's say that I have a different kind of query structure where I want to go and say, can you give me all the people born on a given date, right? In which case what I'm looking for is basically all the entries corresponding to a given column, okay. Now there are databases that sort of specialize in that. They just change the way the data is stored so that they are better at answering these kind of queries, okay. Those are called column stores. There are variants on this, otherwise called also wide column stores, where a large amount of data is stored inside a single column, right? And if you actually need to go inside, you need to go and look up the entries inside the column and figure out what is it that actually matches with your query. And finally, we have this other notion of something called a graph, right? So the idea of a graph is easy to explain. Let's say there is a person A, and person A knows B and C and D, right? C and D also know each other, but none of them know B, right? This is an example of what Facebook is, right? It's basically the friend of a friend network, or the social network that we are talking about, right? There are some people who know lots of others, there are some who don't know many other people, but now I can sort of try and form a relationship, right? How do I get from B to C? And the answer is go through A. So if B and C want to talk to each other, maybe they can ask A for an introduction, okay. So those of you who have a LinkedIn account, for example, might have noticed that this is a third degree connection or a second degree connection. Ask so and so to introduce you, and so on, right? This is exactly what it's doing. It builds up a graph internally which has all of these connections, and then based on that it's able to say, okay, if B wants to talk to C, the best way, rather than just sending C an email and hoping that C will respond, is to ask A, can you introduce me? And then C is more likely to respond, okay. So in these kind of graph structures, the kind of queries that you are interested in are not really give me all people with the name starting with A. Instead it is, what's the fastest way to get from B to C, okay. It could also be a map, right, a world map, and you want to find out the shortest path to get from one place to another, right, or the cheapest set of flights that will get you to London, okay. So things of that sort are graph oriented queries, and there are databases that sort of specialize in that, right? I mean, there is something called Neo4j, and there are other databases as well, which come up in different contexts that sort of specialize in this kind of data storage and retrieval, okay. And one last thing is so-called time series databases, okay. Now these are very application specific. They are typically used to store some metric or values as a function of time, okay. They are useful for things like log file analysis, performance monitoring, and so on. And the kind of queries that you are likely to face over here would be something like, how many hits were there to this website between, let's say, January and March of this year, okay. So it should be able to do a very fast time based query, right? Or it might be that what's the average number of requests per second. So time sort of becomes something fundamental. The problem is if you store every single query and just sort of go back and say, okay, I'll put everything into this huge B tree and then I just have to search through it, because time after all is ordered, right? I mean, there is a clear sense of order over there. That's not very efficient for this kind of structure, right? There are better ways of storing it, and that's where the so-called TSDB, the time series database, shines, okay. There are many examples of this, and part of the thing about TSDBs is that you may not want to store data indefinitely. Let's say after 1 year, I don't really want to store every single thing that happened, every single query that came on my website. I just want an aggregate. I want to know how many queries were there in December, right, rather than on December 13th between 1 p.m. and 2 p.m. okay. So things like RRD tool, the round robin database tool, that was more or less the first one that started applying these concepts on a large scale. But nowadays there are many things such as InfluxDB, Prometheus, and so on, which are coupled with search engines, right, Elasticsearch, Grafana, various things that you might come across at various points, whose main job is to sort of help with analytics, okay. So they can sort of take in log file data and construct time series databases out of it and then allow you to have very interesting queries on your data that come up with good predictors of what is likely to happen, or ways by which you can optimize your application better. So after all of this, right, now clearly those of you who have read more about these things, you would have come across this term NoSQL in the context of most of these alternative data storage mechanisms that I mentioned earlier, right? Now NoSQL, what exactly is it in the first place, right? It started out as an alternative to SQL, right? So it was pretty much when they came out with document databases, they said, look, we are able to store data, but we don't need that tabular structure. So this is not an SQL database, this is a NoSQL database, right? But SQL is just a query language, right? It can be adapted for any kind of query, so including from a document database, right? So what you will find these days is that even for something like MongoDB, the query structure that is used is very similar to what is used in SQL, right? You have select star and various kinds of things of that sort, which are clearly inspired by SQL, if not directly a derivative of that. Okay, so nowadays you see that the term is more appropriately described as not only SQL. Okay, what they are trying to convey over here is that this is not limited to the kind of SQL queries that are possible on a RDBMS, right? And you don't in particular need to worry about things like inner joins, outer joins, and various other ways of constructing a query. What you should be looking at is, are there other variants of the query language that are more efficient at looking up things in the particular data store that we are using here. Okay, so NoSQL, right, and I want to emphasize this, it's not that it's a it's not sort of saying this is not SQL, right, or that it's sort of violating any of the principles of SQL, or that it's not an RDBMS. Generally speaking, yes, that is true, but that's not the point. Okay, NoSQL is just sort of saying that something which is described as a NoSQL database usually has something different in the way it is storing data, which means that using the traditional SQL type of queries may not be the best way to handle it. Okay, and one thing which again comes up in this context is there is this notion called ACID, which once again you might have come across in the database course, and it essentially relates to one of the core principles of databases, which is what's called a transaction, right? And a transaction could be something like create a new user entry, right? So what does that mean? It means basically provide space in the database, put in the user's name, ID, address, phone number, whatever, all of that information, and make sure it has got stored into the database. Okay, and ACID essentially refers to 4 of the principles that are there, that a particular operation such as this should be atomic. Either the entire user entry got created or the database was left unchanged. That it is consistent, meaning that you can't have 2 copies of the database having different information at any given point in time. Okay, isolated, one series of transactions should not sort of interfere with another series of transactions which is happening, right? The result of a transaction should be independent of whether something else happened in between or not. And finally, durable, also to indicate that it should actually get saved to permanent storage at some point. Now in all of these, this consistent part of it is probably the hardest one for a lot of databases to manage, especially when you want to start scaling. That is when you want to increase the number of entries or increase the number of servers that are going to answer a query. Okay, and what happens is that many NoSQL databases sacrifice some part of this ACID. For example, they use something called eventual consistency, right, instead of direct consistency, in order to get better performance. That's not to say that NoSQL means it does not ACID compliant. There can be ACID compliant NoSQL databases. In other words, I can take a document store, right, and say that I still need to have the ACID properties on it. Okay, there's nothing preventing that from happening. So it's not that a NoSQL database necessarily violates ACID, or that anything that violates ACID is a NoSQL database. You need to be a little careful about judging what is or is not a NoSQL database. Okay, unfortunately, it also suffers from a little bit of buzzword hype, right? Meaning that people sort of want to call something a NoSQL database just so that people will look at it, right? That's what is more important is what does it actually give you, which is beneficial. So why do people even want to sort of break the ACID rules? Because after all, they sound like a good idea. The main reason is that consistency is hard to meet, especially when you want to scale up, right, or scale to multiple servers, right? And there is another principle called eventual consistency, which is actually much easier to meet. So to take an example, let's say that A and B, right, are two people. One is located in India, the other is located in the US, and they both add C as a friend on Facebook. The order in which it actually gets reflected in Facebook's database does not matter too much. Okay, so it might be that for a short amount of time, right, someone looking at the page would see C is a friend of A, but doesn't show up on B's friend list. But somebody else might see that, you know, C shows up on B's friend list but not on A's. After some amount of time, C will show up on both. That's what eventual consistency is, right? It doesn't sort of guarantee how fast, or there may be guarantees on, you know, within so much time, but it's definitely not going to be instantaneous. Okay, and the whole idea is that, you know, this is in general not a catastrophe. Of course, nowadays you can't say for sure, right? People might get upset that they were on one person's friend list but not the other, but that's not what eventual consistency is trying to solve. Okay, now on the other hand, a financial transaction where I debit 100 rupees from A's account and credit it to B's account, they have to be absolutely ACID compliant, right? The consistency is paramount over there. At no event should I be able to look into the database and see that 100 rupees was deducted from A but not added to B. Okay, it has to be somewhere, right? So that thing has to be very clear, and especially financial transactions therefore never really go for things like NoSQL. On the other hand, a lot of web applications these days don't require this kind of consistency, and that is why NoSQL is becoming popular now. Now, a quick word on how data actually gets stored, right? And this is that, you know, as far as possible, you would actually like to store data completely in memory, right? Meaning that in the RAM of the system. It is obviously going to be fast, but does not really scale across multiple machines for the simple reason that if I have different machines, right, they don't share the same physical memory, right? So I can't replicate memory as easily as I can let them both share a disk, for example. Okay, but now if I want to store data out to a disk, remember the high latency is associated with disk. This means that I need to change the data structures and organize my data differently.